Welcome back to the NET Physics series. And so today we'll be focusing on the chapter number 6, which is of fluid dynamics. We'll focus on some of the past paper questions of fluid dynamics. So here we have question number 1, and the question reads, which of the given has the least coefficient of viscosity? So now recall, what is viscosity? The coefficient of viscosity measures how viscous something is. So how much friction, you can think in terms of friction, how much friction is present in the flow, right? So friction, you can say it friction to the flow. Now, how easily something flows means the friction would be less, and hence the coefficient of viscosity would be less. So something that flows easily, that means that there is very less friction to the flow of that substance, and hence the viscosity coefficient will be low, right? So basically viscosity, you can think of viscosity as a parameter which measures the thickness or the thinness of any fluid, right? So now we have options: milk, charcoal, water, and engine oil. Now, engine oil has viscosity. If you think about any oil, it flows more with more friction relative to water. So we'll compare everything with water because water is an everyday use of substance, right? So any oil, engine oil or any oil for that matter, has some friction to its flow when it's compared with water, a significant amount of friction. Similarly, if you pour a milk into the glass and you pour water into the glass, you realize that the milk would pour more with more friction, so it pours with more viscosity, right? So it's, you can think of it as it's slightly thick. Similarly with charcoal, charcoal is very thick instead. Now charcoal, when you pour charcoal, it's a black carbon like substance which is pretty thick. So the only reasonable option over here is water, because water is very thin. You can easily pour water, and we deal with water in everyday life. So we all are aware of the fact that it's pretty there is almost no friction with water, right? So we can select that as the correct option. Now, the next question is question 2, which says that terminal velocity is. So they're asking you about the definition of terminal velocity. Let's look at some of the options. It is uniform, it's uniform and maximum, it's just maximum, or it's neither uniform nor maximum. Now, terminal velocity was defined as, imagine you have a spherical body and this falls down, right? So the spherical body is falling downwards. Now, because there is some acceleration due to gravity, there will also be in a practical case, there will also be some air resistance, or you can say some drag to this motion. Now what would happen is that this spherical body, it would basically gain some speed due to this acceleration of gravity. It would gain a speed, and that speed would become constant. And that's the reason for that is, at that time, this weight of the spherical body would be exactly equal to the drag, and hence these two would become equal, and the net force would vanish. Now when the net force vanishes, so it gains a it it attains a constant speed, and that speed is known as the terminal velocity. So this speed which it gains, it would be uniform, and it would be the maximum speed that the object will have, right? So it would also be the maximum velocity. Now you might think, why maximum, right? So the reason for that is, in a practical case, there is always drag acting on the body. And whether be a practical or an ideal case, the weight force will be always there as long as there is some gravity, right? So when this object falls, the maximum speed that it can have is when the force of the drag and the weight of the object becomes equal, right? So that's speed is also called terminal velocity. Hence, it is the maximum and a constant speed. So the correct option is option C. Now, let's move on to question number 3, which says, when body moves with terminal velocity, the acceleration in the body become what? So we just looked at this diagram and we said that the net force is equal to 0. Now we know from Newton's law that the net force is equal to mass times acceleration. So the mass is not going to be 0, right? So that's not 0. But if the force is 0, that means one of these things have to be 0. So that has to be acceleration, right? And again, because we discussed this, that the terminal velocity is constant or uniform, hence the acceleration must vanish. So the acceleration would be 0, and hence the correct option is option A. Right. So now with that, let's move on to this question. Question number 4, we have a fluid is undergoing steady flow. Now we have a fluid and it's moving in a steady flow. Therefore, we have some options. The density does not vary from point to point. The velocity of any given molecule of fluid does not change. This is basically the flow is not uphill or downhill. The velocity at any given point does not vary with time. So to get the correct answer to this problem, you should understand what do you mean by steady, right? Steady is the main key point over here. Now, steady just means steady implies that the time rate of change, which is the derivative with respect to time, this is equal to 0, which means that the function or any variable, in this case its flow, will not change with time. So steady involves time. So for all the options, we don't have any direct link with time. So density doesn't care about steady flow or unsteady flow. Similarly, the velocity of any given molecule of the fluid does not change. So that's also not directly linked with time rate of change, right? So the velocity at any given point does not change or does not vary with time. So this option is more sensible compared to option B, because in this one they specifically mention that it does not change with time. Hence the correct option is option D. Next we have question 5, and this is an important question, by the way. So it reads that the diagram shows a pipe of uniform cross section. So this means that the area of this pipe, circular pipe, is constant everywhere in which water is flowing. So what the substance that goes inside and is going outside, it's water. The directions of flow and the volume flow rates are shown for various positions of the pipe. So here the water flows in this direction, in here it's flowing in this direction. So these are not clear, let me just make them clear. So here it's this direction, here it's this direction, and right, so on. So that's given. Now volume flow rates are also given. So that just means how much volume is flowing inside per unit time. Now the direction of flow and the volume flow rate in the portion marked AR. So what is A? It's over here. So we need to tell what amount of water is flowing either in or it's flowing out. So we need to tell the directions and we need to specify the magnitude of the volume flow rate as well. So think about this problem now. Remember, due to continuity equation, it implies that if anything goes in, it should come out as well. So sum of everything that is going in is equal to the sum of everything that is going out, right? So we'll sum over this thing and we'll equate them. Now, if that was not the case, that would mean that something basically stayed inside. So equation of continuity still implies. Now we'll use that principle, the equation of continuity of flow rate, and we'll deal with this problem. So let's see. What do we know? We know that 6 centimeter cube per second is going inwards. 3 is going inwards. 5 is going inwards. 4 is also going inwards. How much is going outwards? 3. 3 is going outwards. So what about A? What's happening? Is it going inwards or is it going outwards? And how much of it is flowing? So what you can do is, we'll start with this. We'll say that let's suppose that it's going inwards. So here we have some options as well. Downwards 3 centimeters cube per second. Upwards 7. Upwards 11. Downwards 15. So let's see. If we choose upwards, then we should either get 7 or 11. If we don't get any of that, then that whatever we get is not in our option. We'll check. So let's see. 6 is going in. So let's write for in is equal to out. Sum. So what is going in? 6 is going in. 3 is going in. So plus 3. 5 is going in. 4 is going in. And let's say at the moment, let's say that at this point it's going in, right? This is just an assumption. So you're making an assumption. If let's suppose that if it's going in, so then you would put it over here. So plus A. Now we need to figure what A is. And what is going out? We have 3 and nothing else. So 3 is going out. So this cancels 3 like this, and we have A is equal to, you can bring this A over here, so you'd have a negative sign then with all of these things. So this means negative 6 plus 4 plus 5, which is negative 15 centimeter cube per second. Now we chose that A is going in, right? Now that is giving you a negative sign. That direction inwards is giving you a negative sign, which means this negative sign is dictating that the direction which we chose, because you see that it's not in your options as well, this negative sign is just dictating that the option that I chose, the correct option is the inverse of that direction. So the direction should be like this. So this negative sign dictates that. So hence this means that at A it's 15 centimeter cube per second, but it's outwards, right? So if I remove this negative sign, then I say that the direction flips and it's outwards. So the correct option is option D. Right? So we have outwards 15 centimeters cube per second. You could have also maybe we assumed, suppose, what is the other way? Suppose, let's say that you assumed that A is, the direction is outwards. Then in your sum in is equal to sum out, you would say you have 6 plus 3 plus 5 plus 4, but we would not put plus A, right? Because A, we are saying now that A is outwards. Suppose A is outwards. And so in outwards, we would have then A, and then we would have 3. So this would just get rid of these 3's, and A comes out to be 6 plus 4 is 10 plus 5, 15 centimeter cubes per second. So you see now there is no negative sign, hence, which means that the outwards direction for A was the correct direction. So you get 15 centimeter cubes per second and the direction is outwards. So in both cases, we get the same thing. So the correct option is D. Next, we have this question 6, which says that when fluid is incompressible, what happens then? So we have velocity of the fluid is constant, density of the fluid is constant, flow of the fluid is along a straight line. Well, that's clearly nonsense, because the incompressible thing does not really describe that the fluid is moving in a straight line or in a zigzag path or whatever, right? So, and then we have a volume of the fluid is constant. Well, the incompressible fluid is defined where the density of the fluid is invariant or it's constant, right? So when one is applying some pressure to this fluid, the density does not change. Now, in reality, there are not really any substances like that, but we can assume some substances to be incompressible. For example, liquids can be assumed as incompressible fluids. Now, in terms of velocity, the relation with velocity is such that when the ratio between the flow velocity and the speed of sound, it's less than 0.3, right? So if then this ratio is less than 0.3, then the fluid is incompressible. Now, we don't see that over here. We just see that the velocity of the fluid is constant. So that does not have to do anything with the incompressibility of the fluid. Hence, according to the definition, the correct option is C, which says that the density of the fluid is constant. Perfect. Okay, so with that, let's move on to question number 7. And question number 7 reads that an ideal fluid flows through horizontal tube of variable diameter. The pressure is lowest where we have options: velocity is the highest, diameter is the largest, diameter is the smallest, or both A and B, where velocity is the highest and diameter is the smallest. So let's see. Suppose that this is the horizontal tube, right? And let's imagine that there is some cross section over here and the fluid is flowing. right? Okay, so the diameter can be varied. So let's just say that this you can basically shrink or expand the pipe, right? So that's the diameter. So if you recall the Bernoulli's equation, which we discussed in the theory part, um, it was something like P plus 1 by 2 rho V squared plus rho GH is a constant. Now in our case, the height is constant. So basically there will be no change in height. So this term, the change in pressure from here would be 0. So we are left with P plus 1 by 2 rho V squared, which is a constant. Now according to this equation, if the diameter, which is in terms of density, if that is the smallest and if the velocity is at its maximum value, in only that case the pressure will be at its lowest value, right? So the correct option is diameter and velocity. So both A and B are correct. So diameter should be small and the velocity should be high. Only then the pressure is lowest. So these two should be at the same time satisfied for pressure to be lowest. So both A and B are the correct option. So we'll choose D. Right. So next question, we have question 8, right? And it says equation of continuity is obtained by applying law of conservation to what? Law of conservation of what? So equation of continuity, we have mass, energy, momentum, or all. But remember, continuity basically describes, again, if I draw something like this, it describes how much of something is going in and then how much of something is coming out. So whatever amount goes in has to come out. Now, energy and momentum does not really specify such quantity. We have mass. Now remember that the equation of continuity, even in our notes or theory section, we derived it using the conservation of mass. Now, conservation of mass of what? The conservation of mass of any fluid that flows inside this area, or you can say control volume, and it flows outwards from this. So the mass has to be conserved, right? So whatever is flowing in should be flowing out as well. If it's not, then the mass, according to conservation of mass, it stayed inside over this object. So the equation of continuity is then obtained by the conservation of mass. Now, moving on to next question, we have 9, where we says Bernoulli's equation is obtained by applying law of conservation of what? Okay, so this is an interesting one. So remember, the Bernoulli's equation, to derive this equation, the equation is, if you remember, it's again half a P plus half rho velocity squared plus rho GH. Now these are all basically mechanical energies, right? So we have this one, we have this. Now these are basically energy per unit volume, right? But they are energies. So we apply the conservation of energy, or specifically the conservation of mechanical energies, and then we obtain this equation. Now in this equation, if you remember, we discussed this, that uh, this P is the pressure energy per unit volume. This thing is the kinetic energy per unit volume, while this is the potential energy per unit volume. So we are applying the conservation of energy to obtain Bernoulli's equation. Moving on, we have question number 10, and it reads, laminar flow usually occurs at speeds which are what? Low, very high, high, sometimes high, and sometimes low. Now remember, laminar flow was something where you have all the layers on top of each other like this, and they're moving smoothly. So the layers are arranged in a smooth manner. This was laminar flow. While turbulent, if you remember, it was a flow where all the layers are going over each other and they're not smooth as well. So that's turbulent. Now, if you want your flow to be as smooth as possible, you have to make sure that the speed of which at which the fluid is flowing, the speeds are small. So then only you can make sure that the layers move in a smooth way on top of each other, right? So the layers are separated like this and they're moving smoothly on top of each other. So the laminar flow, it usually occurs at speeds which are low. They don't have to be high, of course not very high at all, and you cannot really have a laminar flow where sometimes the speed is high and sometimes it's low. That is also a turbulent flow, right? So the smoothness keeps changing, hence the flow is not smooth at all, and hence it's not a laminar flow, it would be a turbulent flow, this one. So for laminar flow, your speeds should be very low. So the correct option is A. Next, we have question 11, the final question, and it says that a person blows across the top of an arm of a U tube partially filled with water. The water in that arm, what happens to it, right? So a U tube is something like this, right? So it's also called a manometer. Wait 1 second, what happened? Let me use this area eraser. So it's something like this, right? And now suppose there is some liquid or water, right? So it's filled with water and there is water in this. Now if a person blows across, for example, let's say this arm, so he blows across this arm, so what happens is that there would be some air in this region, right? Now as soon as he blows across this, what he does is he creates, you can say, a partial vacuum in this area. So what that does is, because the atmospheric pressure acts from all sides, right? So it's acting from all sides on this, and because this is open from here, so it's acting from here as well, right? So what will happen when it blows the across this arm? That would basically create a partial vacuum, and because there is atmospheric pressure from here, and now there will be some change, because now here there is some less pressure and here there is more pressure. That change in pressure would basically push this water downwards over here, which would in turn cause it to rise from this arm, right? So then this means that the water in that arm would rise slightly. Of course, it would not drop, and rises if the blowing is soft, but drops if it's harder. Of course, according to the concept that I explained, that makes no sense. It doesn't matter how hard or soft you blow. All you have to do is create a bit vacuum over here, which would cause this pressure difference to push this liquid or water upwards in this tube. Remains at the same height? Well, of course not. So the correct answer is it rises slightly. So that's option B.